officers, who's our neighbor, whose offices are right here. Joel is an internationally recognized expert on travel demand modeling. He specifically focuses on deploying and development of activity-based models for large-scale metropolitan areas. And today is going to talk about pricing and reliability enhancements in the San Diego activity travel model. Thank you.
Thank you. The last presentation I saw here at PSU, the presenter had a picture of her office. I don't have a picture of my office, but if you want to know where my office is, if you go out to the top floor of the building and just look north a block across St. Mary's, you'll see our office on the 10th floor of the building, just north of St. Mary's. I'm going to talk today about a project that I've been involved in with the San Diego Association of Governments. And the project involves enhancing their travel demand model to better model pricing and reliability. There are a number of aspects of this work that I'm going to talk about. One is that the models are enhanced to reflect heterogeneity in the traveling public in terms of their sensitivity to travel time. So I'll talk about that a little bit. I'll also talk about the mechanics of how this was implemented in their travel model, and specifically talk about how value of time plays a role in travel demand and the analysis of pricing infrastructure. And I'll talk about how we looked at reliability in the network using INRIX travel time data and how we incorporated that analysis into the model. A lot of this work is based on or stands on the shoulders of previous work that was completed under the Strategic Highway Research Program, the SHARP C10 and C04 tracks, C04 in particular, and L04, which focused on reliability. So this work was funded by a relatively small $150,000 SHARP grant provided by the federal government to SANDAG to move this research into practice. Why does SANDAG care about these enhancements to their model? Well, it turns out the San Diego region actually does have two existing priced facilities, highway facilities. The I-15 corridor, which is a managed lane corridor, also called the HOT corridor, high occupancy toll facility, which is initially opened as a demonstration project in 2007, 2008, and eventually turned into a full-fledged HOT facility about 4 or 5 years ago, and it's been expanded ever since. And SR-125, which is not shown on this map, but it's at the southern portion of the region, just north of a border crossing at Otay Mesa, which is operating as a toll road. So it has two toll facilities and additional managed lane facilities under consideration. And as SANDAG tests alternatives for the regional transportation plan, they are interested in moving the state of the practice in terms of their technical analysis forward. So that's why they care. So I'm curious, how many people here are familiar with travel demand models in general and activity-based models specifically? So first, travel demand modeling. How many people here are familiar with travel demand modeling? How about activity-based models? Okay, some. Okay, so let's, I'll just quickly go through these slides here. I've got a couple slides sort of explaining what an activity-based model is, and then I'll talk about our enhancements to the model. So an activity-based model is a model that represents travel by individuals as opposed to travel by groups of segments. So trip-based models deal with segments of population, segments of household. Activity-based model deals with individuals. Secondly, activity-based models model travel as part of tours. So it considers trips in a sequence as opposed to trip-based models in which trips are treated completely independently of one another. And thirdly, activity-based models schedule travel and activities in time and space consistently. So they recognize that no person can be in two places at one time. In activity-based models, the process of modeling is a little different than the process of modeling in trip-based models. In activity-based models, we generate a database of households and people that represent the population that we are trying to model. Okay? So we generate this synthetic population for the region. And then we apply our models to that synthetic population. And in the trip-based world, the models are applied through what we refer to as aggregate probability accumulation. So we have probability distributions, models produce probability distributions, and in the trip-based world, we multiply the probabilities by the segments and accumulate those results over a number of dimensions to get at responses. In the activity-based model world, we generate the same sorts of probability distributions, but instead of multiplying them by the segments, we make specific choices for each person and household in our database. And that becomes the result of the model. That's called Monte Carlo simulation. So it's a key application difference between an activity-based model and a trip-based model. Okay, so I mentioned that this work follows on work that has come before it. There have been a number of other studies that have enhanced their activity-based models to deal with pricing enhancements for San Francisco County, for the Chicago region, for Sacramento. And on this slide, you can see a plot that shows values of time for different income groups. And these values of time are distributed. So there's a probability density distribution that reflects variation in values of time. So this is very different than the way a trip-based model would deal with value of time, which is through segments. Everyone in a segment sees the same value of time, an average value of time for the segment. And in these activity-based models, the values of time, how much people are willing to pay to save time, they are distributed. So one person can have a very different value of time than someone else. This is the equation that is recommended by the Sharp C04 research to reflect, properly reflect time and cost in the utility of highway, of traveling on highways or any auto alternative. The utility is a function of the time, which is the first component of the equation, and the cost, and so the time here is distributed, okay, according to the same sort of distribution I showed on the previous slide. It's a function of the cost, and the cost is scaled by income and auto occupancy. So wealthier households are less sensitive to cost. Lower income households are more sensitive to cost. And the higher auto occupancy is, the less sensitive you are to cost because there are more people in the car upon which that cost is averaged. And then finally, there's a term in here that reflects reliability, which is expressed as the standard deviation of travel time over the distance for the trip. So it's a unit variation in travel time. And then finally, there's an alternative specific constant, which is turned on if this facility that somebody's contemplating using is a toll road, to reflect biases not reflected in time, cost, or reliability that either increase the utility of travel on the toll road or decrease the utility of travel on the toll road. So going back to the previous equation, there was a term in there that scales the cost by household income. So this plot shows how that is reflected in the equation. It compares the cost sensitivity at various household income levels to the cost sensitivity of an average income household for San Diego, which is somewhere around 50K. So you can see that very low income households are between 3 and 4 times as sensitive to cost as a average income household, and a traveler from a very high income household is maybe half as sensitive to cost, all of the things being equal. The Sharp research recommends using distributed time sensitivities, but it is not specific about how to specify those distributions. So we at RSG have done a lot of stated preference surveys of toll demand throughout the country, looking at how much people would be willing to pay for toll facilities. And it's very common in these studies to look at distributed time sensitivities. So we were able to compare this research and calculate what a distribution should look like from that research. So here is what the distributions of value of time, also referred to as willingness to pay, looks like after the models have been implemented for the population in San Diego County. And there's 2 plots. One is for work travel and one is for non-work travel. But as you can see, they're pretty similar. Okay, the work travel one tends to be a little flatter. That is, there's more people willing to pay more money to save time if they're traveling for work than the non-work distribution, which tends to be a little bit more peaked. But the distributions are quite similar. Now, when this is actually all applied in the disaggregate models, the activity-based models, where we sample from a distribution for time coefficients, and we calculate the cost according to the person's income and their auto occupancy. But these models still rely on what's called static equilibrium methods for traffic assignment. For once the activity-based model generates all of the auto trips, those trips are still aggregated into matrices and assigned to networks. So from that process, we still have to aggregate the results into bins, similar to what we might do in a trip-based model, but only for the assignment step. To calculate what those bins should be, we divide the distribution into percentiles, and we use the 33rd percentile as a breakpoint for the low-income bin, for the low to medium-income bin, and the 66th percentile as a breakpoint for the medium to high-income bin for assigning these trips to a path in the network. So that way we get roughly a third of the trips in every bin. Now I'm going to talk about the calculation of reliability in the models and how we looked at reliability through our INRIX data. So the C04 report talks a lot about reliability and a lot about the research that's been done, but doesn't provide much guidance in terms of how to actually implement reliability in a travel demand model, just because there hasn't been a lot of research into the calculation of reliability in practical terms for implementing it within a regional model. There's a lot of work out there on reliability for specific facilities, for specific corridors, but not a lot of guidance for how to make it work in a practical sense. And so actually, big picture, a lot of the work that was done under this project for SANDAG was looking at this research and trying to think about how to make it work in a practical sense in this tool that SANDAG uses literally every day for project analysis. One of the recommendations in the C04 report was to estimate reliability factors simply based on the volume to capacity ratios on links. So in other words, more congested links are less reliable. Therefore, the reliability could be inferred as an extra delay factor on top of the delay that is caused by simply congestion. But this isn't a very good way of measuring reliability because, first of all, research does indicate that the unreliability of a link isn't exactly linear with respect to congestion, that as you reach higher congested conditions, that unreliability sort of plateaus. So that's one consideration. Another consideration is that there are lots of other factors besides congestion that increase the unreliability of a facility, and we're going to look at those through research. So to explore this topic further, we acquired an INRIX travel time data set for San Diego County. There were about 3,000 TMC segments. These are segments that have been used for a long time. They stand for Traffic Management Channel segments. And they were originally developed for deploying emergency vehicles, but a lot of the travel time companies that produce this data have adopted them for specifying travel times for facilities. Unfortunately, they're not perfectly coincident with the transport networks we use, so we had to go through a pretty extensive process to take the data and allocate it to code it to the travel demand networks, the transportation networks, which tend to be a lot more detailed than these TMC codes. And you can see the freeways and arterials are pretty well represented, but there are very few data points for ramps and other smaller facilities, lower class facilities. So this gives you a sense for what this INRIX travel time data looks like. It's essentially a sampling of GPS cell phone data, travel speeds captured from GPS data for an entire month. And the month that we are looking at here is October 2012 for each facility by time of day. So you can see here that on the top, most of the points are down here, except for in the peak periods, you get a bunch of higher points. In other words, it took longer to traverse this particular TMC segment. And as you might expect, because in the peak period, presumably the peak direction is the PM, that it's more congested. And so what we're looking at is the variation of this data, right? The standard deviation. That is an expression of reliability. One of the things that's important to do when you work with travel time data, because it's quite messy, is to go through a process of trying to identify outliers in the data. So I won't spend a lot of time with this, but just suffice to say that we did go through a process of removing outliers. And you keep in mind as well that the travel demand models that we're using do not represent what you might refer to as non-recurring congestion. That is, congestion that arises due to major incidents on freeways that shut down freeways, or extreme weather events. Okay, so when we see that in the data, we want to make sure, or construction. So when we see that in the data, we want to make sure we filter that out. This is what the standard deviation of travel speed looks like after the data has been cleaned and attached to the network, and this is for a specific period, which is between 5:30 and 5:45 p.m. And you can see that on the freeways, there does tend to be higher standard deviations in speed, as you might expect, because the data suggests that there's a lot more variation on freeways. So once we had all this data processed and coded and cleaned and attached to the network, we were able to estimate regression equations that relate link characteristics to the standard deviation of travel time that we see in the data. And this was done by expressing the standard deviation in a unitless measurement. So it's the standard deviation in terms of minutes per mile divided by the mean travel time in minutes per mile. So it is an additional amount of variability based on the average travel speed, essentially. That's how we're modeling this. And the independent variables that we use in our equation are things like travel speed, so the posted speed on the facility, the number of lanes in the facility, the type of control on the facility, so if it's signalized intersection, if it's unsignalized, and so forth. We coded some special variables like the distance to and from major freeway interchanges, expecting that there's more conflict because of weaving conflicts as you approach major freeway interchanges. So we want to reflect that. Volume to capacity ratio, obviously, because as congestion increases, you would expect also variability to increase. And we coded specific what we call shift effects, which reflect the effects of times of day beyond the time periods in the assignment process that affect reliability. So this is a plot of the estimation results specifically with respect to the distance to and from major interchanges. And as you can see, as you approach a major interchange and as you drive away from a major interchange, there does tend to be more variability experienced in terms of the standard deviation of travel time. This is a plot of the level of service by freeways in blue and arterials in orange. And so you can see as the volume to capacity ratio, as the link becomes more congested, you do tend to see higher amounts of variability on the facility, although arterials tend to be much more mitigated in terms of the variability. So arterials tend to provide, according to the data, a more stable travel time than freeways, even at higher volume to capacity ratios. And this is a plot of the time of day shift effects. I won't spend too much time on this, but it essentially demonstrates that the time periods used in the travel demand model are essentially insufficient to represent the amount of variability in terms of travel times throughout the day, because the shift effects are all significant, and they reflect that as you approach the peak of the peak, the variability in travel time does tend to increase, especially on freeways, less so on arterials. So we did perform two estimations with the data, one with the time of day effects, one without. Our estimation without the time of day effects was used because we want to take into account, we can't take into account the shift effects in the travel demand models because the travel demand models are limited to 5 time periods for assignment. So we wanted to have one estimation without those time of day effects so that we could take those coefficients and apply them in the travel model. So this slide shows the volume delay function that's used in the model. Does everyone know what a volume delay function is? Does anyone know what a volume delay function is? A few people, maybe. A volume delay function is something that's used in the traffic assignment algorithm that expresses how travel time changes as a result of demand. So as demand on a link increases, the delay on that link increases. And this is the equation that reflects that relationship between demand and the capacity of the link and other link characteristics and the travel time on the link. So the volume delay function used in San Diego is a slightly modified version of the classic volume delay function that's been around since the mid-50s, which is referred to as the Bureau of Public Roads, which is the agency that preceded the Federal Highway Administration. They were the first agency to develop travel demand models, and they developed a function to be used in these very simplistic travel demand models that's still being used today. And it's simply an equation that relates the, okay, I'm supposed to use the mouse to point to things on the screen. So the volume to capacity ratio raised to an exponent, which is calibrated based on observed data, multiplied by another coefficient, and you add 1 to that result, multiply it by the base travel time, and you get some level of congestion as the volume increases on the link. And this ratio approaches 1 and then actually can go even higher than 1. So this is the classic BPR function. But I mentioned that Sandag has a modified version of it where they have added a component to reflect what's going on at the intersection. So this part of the equation reflects the cycle length at the intersection and the amount of green time that an approach at the intersection gets, and as the and a signal progression factor in the cycle length. So it's basically saying what is the chance that you're going to get stuck at a red light at this intersection? Okay, so that's an additional delay for controlled intersections. Okay, the chance that you're going to get stuck at a red light times the amount of time that you're going to be stuck waiting for that to turn green. That's what that portion of the equation says. And then there's a third portion which reflects delay at that intersection. So you can see this part of the equation is multiplied by this part of the equation. So as the intersection gets more congested, there is a BPR-like function specifically for the intersection that increases as the demand increases, and then this intersection component is added on to the mid-length component to get the total time of delay on the link. So our approach in taking the reliability equation and implementing it in the model was to modify this volume delay function to include the amount of variability in terms of the standard deviation of travel time through this additional equation. So it is the result of the original volume delay function plus the reliability, the R component, the reliability component, which is equal to this portion of the equation is related to the volume to capacity ratio delay, which is this plot here. So it's reflecting the additional time in terms of standard deviation minutes of travel time occurring because the volume to capacity ratio on the link is increasing, plus everything else about the link that isn't changing in the assignment process. So those are things like the number of lanes and the speed of the link and the distance to and from major freeway interchanges, which are all static throughout the assignment process. They're not changing as a result of volume. So this whole thing is added and reflected in the volume delay function. So the paths that somebody is choosing in the assignment is reflecting not just the travel time, but also the variability of travel time. There are some mathematical issues associated with doing this. I'm not going to get into it. If you're really concerned or want more information, you can go to the report that's on Sandag's website and learn more about the issues associated with additive variances and how to aggregate variances across links and the assumption of independence of variance. So there's more to this that I want to get into, but it's definitely a key issue in modeling reliability that has not been solved yet, and we did not solve it as part of this project. This plot just shows how the standard deviation of time varies with respect to travel time. So you can see that the standard deviation of travel time ranges between very low 0 minutes and 20 minutes, whereas the travel time for certain interchanges, zone pairs in the model, can be quite high. Okay, so after one implements all this stuff in a travel demand model, it's always important or useful to go through an exercise of validating the model against observed data. How well did this model improve the results of the model? How well does it better match observed data? And does it improve the sensitivities of the model, or are the sensitivities of the model appropriate when it's used? So I'm going to talk about that process now very quickly here before we conclude. As I mentioned, there are two facilities, existing toll facilities in San Diego, so it really does make San Diego like the perfect region to test enhancements like this, because there is existing toll demand in the region. The I-15 facility is a hot lane, as I mentioned, and SR-125, the South Bay Expressway, is a toll road. Okay. This plot shows the results of the model in predicting demand on specific segments of SR-125, which is the toll road, in the northbound direction. I'm not sure what time period. This must be all day. Yeah, I think this is all day data. So the dark blue bars are the observed data. So Sandag actually owns and operates and maintains this facility. So they have a lot of data. The blue bars are the observed toll demand in terms of vehicles. The light blue bars are the original model results. And the brownish-hued bars, I guess, are the estimation results, the results of applying the model. And one thing that you can see is that the initial model tended to underestimate the demand at the southern segment of the facility and overestimate the demand at the northern part of the facility. The new model has a similar trend, but it's much closer to the observed data. So that's really good. The other thing you can see here on the estimation results is that we can see through the assignment process the proportion of demand that is in the medium and high value of time bin, because we're assigning those trips separately. So we see on this facility, there's absolutely no low value of time demand. That's probably because there are alternative free facilities to SR-125. So the low value of time travelers are taking the free routes. They're not taking the toll facility. It's only some of the medium and high value of time travelers who are paying the toll to save a few extra minutes that's offered by the facility. So that's an additional benefit that you get from these enhancements, as you can tell what's going on in terms of people's willingness to pay for the facility that you wouldn't be able to tell if you had just assigned everyone using an average value of time. And similarly, we have validation results for the southbound direction. And these are similar results, but this is for I-15, which is a high occupancy toll facility where the cost of the facility is being priced dynamically throughout the day to balance revenue and the time that it takes to travel on I-15. And again, you can see the this is just comparing the observed data to the estimation results. The estimation results do match the observed data pretty well, although for certain interchanges we're a little bit low and for certain interchanges we're a little bit high. But overall, the match is pretty good. And this is the southbound direction. There are a couple key interchanges where we are underestimating demand, and it's likely that we need to look into that a little bit more to understand, why exactly is the model underpredicting demand for those specific interchanges. So that's part of the validation process. That's the part of the validation process where we compare the model results to observed data. The other part of the validation process is called sensitivity testing. When we vary key inputs to the model, we run the model, we look at the output of the model compared to the base case, and we look at things like elasticities. How is demand changing with respect to this change in the inputs? And there's a wide body of literature out there on the observed elasticities with respect to toll changes that we can compare the model results to make sure that the model is behaving appropriately. So we ran a couple of tests, the base case, which you saw the results of, plus we ran a test where we took all tolls and we cut them in half, and we ran the model for that. And then we did another test where we took all the tolls and we doubled them, and we looked and summarized those results. So we get a range of results in terms of toll costs. And then we looked at the literature out there on toll costs, elasticities, and compared our elasticities to the literature. So we did see through this process a pretty reasonable change with respect to toll changes. But we did see fairly high elasticities with respect to toll price decreases compared to toll increases. Now, that probably goes back to, if you look at the value of time distributions, you see that they're right skewed, which means that there's a lot of travelers on sort of the left side of the distribution who essentially have a low value of time, and therefore there's a lot more demand in the lower value of time category. When you reduce the price, you get a lot more of that demand changing. Okay, so it is partly an outcome of using distributed values of time, and it kind of does make sense. You know, if you think about it, there's a lot of people who are clustered around the average value of time, and there's a few travelers who are willing to pay a lot to save some time. Now, if you take a priced facility and you cut the toll for the price for that facility in half, all those people who are clustered around the average, who are maybe priced out at the original toll, they're now much more willing to take the facility, right? But if you double the existing toll, assuming that toll has been priced correctly, which is somewhere around the average value of time, there's less travelers who are out at that tail, and so the change is lower. The elasticity is lower. And so you can see the report if you want to look at the elasticities by facility. Okay, so I did mention the report. It is available on the SANDAG website if you're interested in taking a look at it. You can download it. There's a lot more detail in the report about the model system, what was done, the results of the estimations, the issues with implementing standard deviation of travel time in path assignment and skimming and the travel demand models. It's all in the report, so I'll refer you to that for details. Some general conclusions. Overall, the goodness of fit of the models did improve by implementing these changes. Previous to implementing these changes, in order to match the demand on SR125, we had to have sort of a fudge factor in the models. Through implementing the reliability and the travel time, value time bins in the assignment process, we're able to remove that. So that was a real benefit of the approach, to make reliability implicit in the model rather than something that somebody has to code a priori. And the I-15 model, I didn't mention this, but we also implemented a toll transponder ownership model, because use of that facility is limited to people who have the availability to use toll transponders. There's no cash option on that facility. So to get the demand right on that facility, we had to implement a model to reflect which households had transponder units. And once we did that, we were able to much more closely match the demand on I-15. And I would just say, in general, there's a lot more work that's necessary in terms of understanding reliability, and in particular implementing reliability in both static equilibrium models and dynamic traffic assignment models. questions? Yes.
Regarding you mentioned earlier the price at different income levels be willing to pay per hour. There's lower levels like they're $6, higher levels $50. And you mentioned obviously cut the price, increase the demand, the price of tolls. Are you aware of anybody who's done any work, or that anybody had any luck in pushing that number up, through marketing or publicity of tolls or demonstration of showing that time really are decreased? That hey, we believe it enough. I guess it's increasing the reliability number maybe, but we believe it enough that actually we've moved this group up to willing to pay $7 an hour instead of the $6. Is there anybody?
Influencing people's willingness to pay. Not that I know of. I mean, I will say that the toll transponder unit ownership program has a big effect on demand. And we saw this in the Bay Area as well, where you can get discounts if you have a transponder unit rather than paying the cash option. And so that's one way agencies are getting more people to use these facilities, is they are marketing the ownership of the transponder units more. And I think there's a lot of evidence that suggests that when people own these units, they're less cost sensitive, because you set up the unit with a credit card account, and you can set it up to automatically deduct the toll charges every month, and then it's like you're not even seeing the transaction cost. And so there is certainly research in that area to suggest that. Now, I'm not sure it's the value of time that's changing. I think it's people's perception of the price that's changing. Yep.
On that, what are the politics around having the estimate that there are no low-income travelers on the facility? That must have been quite alarming.
Yeah. It's not that there's no low-income travelers. It's that there's no. But there's, yes, but there's two things that are reflected in the value of time. There's income, and there's time sensitivity. Okay, so I think it would be dangerous to say that there's no low-income travelers on the facility. It's another thing to say that there's no low value of time travelers on the facility, because you can, through the simulation, you can have, and it would be interesting to look at that, look at the demand by income, but you can have a low-income traveler who has a very high travel time sensitivity. So even though their cost coefficient is also relatively high, their time sensitivity is very high. And through that relationship, they're actually placed into the medium or higher value of time bin. It's sampled from a distribution in the sampling of time sensitivity. Income affects the cost sensitivity. Okay, so imagine a parent who has to pick up a child from daycare, and for that particular trip is very time sensitive, right? And so their willingness to pay is high, even though their cost sensitivity is also high. Yes.
Yeah. Leah Anderson. I have a question that kind of goes along with all of this. I'm less familiar with modeling, but I'm interested in how, or if you've done any research on how, like, the current economic environment influences, well, your model. Because that would be, you talked about not using recurrent, non-recurrent things in the model, but something like a recession where people have, like, a cost sensitivity is going to be. Just like how you factor in like bigger movements, like political, economic, things like that into the model, or if you can.
So there are models that attempt to do this. In fact, Oregon is a leader in this area. There is an Oregon statewide integrated model that has an economic component. The SENDAG model does not have such a component. So the synthetic population, when it's generated, you have to specify what the income distribution is for that population. And then and how many workers there are, for example. And you also have to specify, for example, the cost of fuel that people see. So those are all, in this model system, are all specified by the analyst when they're generating the population, running the model. There's a land use and demographic forecasting group at Sandag that is responsible for doing a lot of that work. But there are models that, to one extent or another, take those things into account explicitly in the model system itself. I saw some, yes?
I was curious about your graphs for the work, for the travel time distribution of non-work versus work travel time, and the willingness to pay for tolls. I didn't understand how those could be similar. You said that they were very similar.
Yeah.
I just can't see that.
Well, it turns out that there are a lot of studies that show that, there are a lot of people that value their non-work travel time just as much as their travel time for work. And I think part of that is what direction they're traveling in. So, for example, people traveling to work may have a higher value of time than people traveling from work to other activities, but those are all considered part of the work tour. They all see the same value of time. But I think as people's schedules become busier and busier, their time is just generally valuable to them, and they're willing to pay for priced facilities to save time, even if they're not traveling to and from work. Bud, I saw you. Yeah.
The parent picking up, kid at daycare or somebody on the way to the airport, whatever.
Yeah.
So it sounds like there's a distribution of values of time for individuals,
Right.
But is that also taking into account the varying values of time within one individual, depending upon what they're doing?
Yes.
So there's some sort of aggregation effects there.
Right. So basically what we're doing is we're sampling a factor of time. It's a time sensitivity factor according to a distribution. And then we're applying that factor to the coefficient for travel time for each tour purpose. Okay, so going back to your question too, because these two questions are interrelated. The time factor could be lower for certain tour purposes because they're non-work. Okay. Yes?
Have you looked at, my name is Hamed, I'm mechanical engineering major. Has it been looked at the various time and days and discounted tolls, like say holidays or season days or like weekends versus like after late night or early morning the price of toll? Does that going to affect revenue and the demand?
Yes, in terms of temporal distributions of tolls. Okay, so we do have 5 time periods that are reflected in the model in terms of network characteristics, and the tolls in each time period are different for each. The tolls are different for each time period. So that reflects the differences in tolls by time of day, at least on I-15, which is dynamically priced. Not on SR-125 because it's a flat toll. It doesn't vary by time of day. In terms of seasonal variation or discounts, I don't know that there are discounts on SR-125. On I-15, those would all be reflected in terms of managing the demand, the dynamic pricing algorithm. The travel demand model is very aggregate. I mean, it doesn't have that algorithm. It doesn't represent the algorithm the same way it's being run in the real world. In the real world, tolls are changing every 15 minutes. And in the assignment process, there's just a toll that's calculated based on the real world toll and just implemented in the model. So I don't know if that answers your question, but the model doesn't really understand a lot of that variation in terms of toll price. Yeah.
any attempt to incorporate psychological factors like shame or group identity into this? For example, if you're in a sprawled out infrastructure like Los Angeles, I might not want to be that guy standing at the bus stop as every car passes me. But in New York, you're just kind of part of the crowd. It's not just a matter of congestion at that point. Or group identity. Like, I don't feel comfortable walking through the Pearl District, but if you lower the prices, I might feel like that's a place for me. Analogously, if you charge $100 on a toll bridge, I see that as a tool for upper middle class workers, you know. But if you drop it to 10, it's not just a matter of affordability. It's like, okay, that's a tool meant for me and people like me.
Yeah. So your question has two answers. One is, and I think a more general way to state your question is that there's all these personal preferences and biases that people have to all of these alternatives, right? There's what's called brand loyalty, right? I'm an auto driver and I don't care about transit, or I like my toll road and I'll never drive on those general purpose lanes so long as I can use a toll road. There's other aspects, right, that of bias that people have. And those are reflected in model parameters called alternative specific constants. And they take all those biases and they kind of group it together into one number. Now, we can have different numbers for different groups of people, different segments. So, low auto ownership, high auto ownership, they all have different biases. But those numbers, those are all in the model. Okay, and how do we calculate those numbers? Well, we can estimate them using statistical inference. Or we can apply our models and adjust them, and it's essentially saying, hey, there's all this stuff out there that the rest of the equations don't represent, that are influencing how many people we observe making these decisions. So we can adjust these coefficients, these parameters in the model, to match the number of people who we observe making these decisions, and whatever that value is in that coefficient, it represents all of those things. So that's one answer. The other answer is you were asking about, like, I might be willing to take it if the toll was a lot less. That is reflected in the value of time heterogeneity. Okay, that you're absolutely right. People have different preferences, and that's exactly why we want to model a distribution across the population. Okay. Any other questions? Yeah.
Your elasticities that you showed?
Yeah.
Are the tolls here variable by time of day or otherwise within the system?
They vary by time period for I-15, not SR-125, because SR-125, they're flat tolls.
The congestion on the road is well in any form?
The observed tolls do, because the algorithm does. In the model, it doesn't. So the tolls that we use in the model are based on the base year tolls. But that is an aspect of the Sandag models that could probably be improved, you know, that you run the model and the tolls dynamically adjust.
And, other studies have been done that show that decreasing variable tolls actually decreases the use of the lane. And as you increase that toll, drivers use that as if it is a signal of congestion and time savings. Therefore, when you raise the price of tolls, you are actually bringing more people into your lane than you're raising the price of tolls out.
Yeah, right.
Yeah. I'm just wondering, did you find something different with your elasticity there? Because you mentioned that when you lowered the tolls, was a greater elasticity because more people were there. So I was wondering.
Yeah, so the models assume travelers have perfect information. So that is another aspect of the model. You know, I'm not sure you would want to have this observed phenomenon in your model, because it would lead to some pretty strange conclusions about policy changes. But it is true that for certain facilities where the variable message signs don't show the difference in travel times, and that they're only seeing the toll price as an indication of the time savings, that they could be, you know, they could have be misled. But you know, in our scenario, we weren't really trying to test. We weren't really trying to test like changes in the toll given the current price. We were really trying to test what would happen if the overall price was cut in half. So I think the sensitivities that we're getting are still, you know, it's still a valid use of the sensitivity. I'm not sure if I'm explaining myself well, but yeah, okay. Yep.
Do you have your relationship between the ABC ratio level service and the travel time standard deviation? Do you have an explanation for this sudden change of trend for a freeway? I think around 1.18 or so, it become kind of much steeper
Yeah.
than before that.
Yeah. You know, it may be a function of the volume delay function itself. It may be a function of just the low number of data points that we observe really high volumes on freeways in San Diego, but there is a realm of instability here that I think the equation's trying to pick up on, where, you know, maybe that section of the curve is when the travel time becomes really unstable in San Diego. Yeah.
I noticed on your presentation that on the I-5, actually there's no low value of time users in the northbound, but on the southbound there are a lot of low value of time users on that segment. So is there any special reasons for that? So
I'll have to go back and see. So we're looking, not I-15? No, not SR 125, you mean? No, so those are both medium and high value of time travelers. So it's pretty symmetrical. Okay? Other questions? Yeah.
Matthew Gray. This could be a bad idea, but how feasible would it be to feed live INRIX data directly into a tolling system to calculate a price based on live conditions?
Well, it turns out that Sandag actually has an ITS group, and they have developed something called an integrated corridor management system, specifically for I-15 and parallel facilities. And that's exactly what they do. They monitor speeds on their facilities. They monitor incidents on their facilities. And they have a model running that is not this model, but a different model. And when an incident occurs, or when there is a really high level of congestion, they can dynamically change the price, but they can also dynamically change traffic signal timing. Or if there's an incident, they can deploy vehicles through the system, you know, emergency vehicles, and they can change variable message signs to reroute traffic. So it's Sandag's a really neat place to work because they really are leaders in travel demand management and modeling, and there's a lot of really cool facilities that and travel markets that are interesting to look at in San Diego. Yeah.
It's a question. It's a modification of a student's question.
Okay.
The max revenue stream for this facility is probably, they can probably adjust it to get it to that. It's maximum flow. It's whatever it is, 40 miles an hour, steady stream. They also manage the non-toll facilities. Do they try and get the system running so that the max revenue point of operation on the tolls? You know what I'm saying? because they're running, they're running on-ramp meters on the non-toll, they're doing other things.
Yeah.
Emergency management.
So I guess the question is I-15 being managed to maximize revenue, right?
But also the parallel facilities. They're not just one link, parallel.
Well, right, because I-15 is a managed lane. There is a parallel general purpose facility. My answer to that is no, it's not being managed to maximize revenue. And the reason for that is because it's a hot lane. I mean, if you think about it, hot lanes are basically giving away revenue. They are allowing HOV2 plus vehicles in this case to travel on the facility, so they're consuming capacity and they're not paying any fee. Now, if they really wanted to maximize revenue, they'd make it get rid of that and make everyone pay. Any other questions? Okay, thank you.